next sessions, I prepared some quite general slides on the OFG setting, that we get a general understanding what we are looking at. I put together a number of case studies where geophysics was used for OFG studies, which published in the literature. So you will see lots of slides on models, so that you get a feeling what instrumentation is used, what are the logistics behind that, how the measurements are done, etc., etc. So what do we know about freshened OFG? We call it OFG, right? You're fine with that. OFG is offshore freshened groundwater. What general information on that? We are looking at a salinity lower than seawater. There have been different definitions on that. Some put some PSU, practical salinity units, to that, what they would consider as freshened groundwater. So here I follow the definition by Mikalev in the 2020 paper, I think. We're looking at salinity less than seawater, around 15 PSU, which is the practical salinity unit, or gram per liter. It occurs within 50 kilometers of the coast. It has been observed way further out. We are here, as to this understanding, it's the groundwater which has been in place during the last glacial maximum. There are other processes where offshore freshened groundwater exists. For example, through submarine gas hydrate dissociation. Gas hydrate doesn't include the salt in the water, so if it dissociates, it's fresh water. So that's something we will not tackle here, since we focus on geophysics methods to look at the offshore freshened groundwater as a resource. It's typically less than 130 meter water depths. That's the that's the water depths, or that's the sediments and water depths which has been exposed along continental shelves during the last glacial maximum or different cycles before that. We are looking at sediment depths from seafloor to about 200 meters below, but in some areas it can be much deeper. So some areas there can be very deep aquifers, even offshore. It's mostly in siliclastic aquifers, but as we have seen in Malta and other areas, there are other lithological environments as well, like karstic or volcanic offshore Hawaii, but it's typically in siliclastic aquifers. That's what we mentioned, emplacements by meteoric research during the last glacial maximum cycles. And it is considered as a so far mostly untapped, globally available resource of freshened water in coastal areas. And the two images, the two figures here originally from Weimar, describe one main questions of offshore freshened groundwater, which is this offshore aquifer, is it inactive, fossil, or is it connected to the land aquifer? And that's one of the main questions we have, and which we try to address with geophysical methods. Key questions, brackets, we think, what we want, we aim to address with geophysics is the volume, the research potential, which is largely unknown, potential of offshore freshened groundwater. To know that, we need the lateral extent, the depth and the thickness of the offshore groundwater layers. We are also interested, do we have salinity variations along the aquifer? And what is the the structural architecture, and the lithology. And what I mentioned just now, is it connected to the land aquifers or isolated? Or in other words, is it active or passive? Some definitions. We heard that. Offshore freshened groundwater, OFG, groundwater stored in pores of sediments or fractures of rocks in the subsea floor, which have a total dissolved solid concentration below that of seawater. How should I put it? We heard this. Lots of you are rather working on near coastal submarine groundwater discharge, saltwater intrusions, or both of that. That's a much larger community who's dealing with that. But we want to be clear when what we are talking about. They're of course connected. There's an overlap looking at this different processes. So submarine groundwater discharge, the flow of groundwater from land to the ocean through the seabed, including both fresh and saline groundwater, delivering nutrients and chemicals to coastal marine environments. So it took me quite a while to understand what's really meant by that. I thought it's just these puddles which occur at the beach or in coastal areas, but it's any water which discharges through the seafloor in the ocean. So it could be diffuse and it could be localized. Let us go to the last sort, seawater intrusion, the process by which seawater encroaches into coastal freshwater aquifers, causing increased salinity and potential degradation of groundwater useful for drinking and irrigation. Now, the point I want to make here is if you're talking about OFG, these are systems which may extend from the coast to the shelf break over kilometers to hundreds of kilometers at depths from the seafloor to several hundred meters below. So to my understanding, or how I see it, is offshore freshened groundwater is huge, can be huge. It's a large volume. And this requires tools and methods capable to cover these areas and extend from seafloor to depths of hundreds of meters, and which can be addressed by geophysics. So my understanding, looking communities below, if you're talking about submarine groundwater discharge, seawater intrusion, it's more a local, comparatively localized features. But to estimate the volume of OFG, we need areas to look at, methods which cover large areas. And that can be done by marine seismics, hydroacoustic methods, electromagnetic and geoelectric, or ERT, electrical resistivity tomography methods. These methods are complementary to each other and can, as we will see in the coming slides, they can cover from seafloor to several hundred meters depths. This is a figure from the publication of Arevalo and Martinez, where the next slides come. This just puts nicely in perspective where freshened submarine groundwater discharge occurs along coastal lines. That's the red dots, and the blue triangles where offshore freshened groundwater has been inferred. So being at meetings at EGU or at the SWIM conference recently, there's a whole community dealing with submarine groundwater discharge and saltwater intrusion. OFG is more a topic which is coming on the brink. And that also depends on the sparse data coverage we have so far. Actually, offshore freshened groundwater has so far imaged by chance, looking at borehole data for oil and gas industry, which has to drill through the freshened groundwater layers, which was more a site investigation for that industrial applications. I have here, the paper also shows some terminologies which might be useful. I don't want to go in detail through that. We talked a little bit about that. If you will get a literature list at one point where you can look at this information. But yeah, just maybe not all of you are too familiar with these terminologies we use here. This is what the slides use, or when we're talking about different issues. OFG, fresh and groundwater. CSEM is controlled source electromagnetics. ERT is electrical resistivity tomography. MCS, multi-channel seismics. HA, hydroacoustic. Yep, so that's, just keep that in mind. The paper also puts together some methods for OFG and freshened submarine groundwater discharge exploration. Again, I don't want to go in all the detail. So these are methods we're going to talk about here, which are also mentioned in the paper. So electrical ground conductivity, seafloor mapping, sub-bottom imaging, this is the hydroacoustics, electromagnetics. There should be some seismics here as well. Hydrogeological modeling is not really something we're going to address here. That has been other training schools, right, which were looking at that. There are also other methods addressing offshore fresh and groundwater exploration, but this is not in the field of geophysics. You're probably aware of these global figures where offshore fresh and groundwater occurs, which has been put together in the well-cited paper by Vincent Post from 2013, where he collected from literature together where offshore fresh and groundwater has been directly inferred, indirectly inferred, and suggested from data. And on the right side, this is the global figure of Mikalev et al. Yeah, these are, if you're interested in the topic, I'm sure you know this publications already, but they're very good to read it. From these papers, you can also get the estimated global volume of OFG, which ranges from 10 to the 5 to 10 to the 6 cubic kilometers. In the Mikalev paper, I was looking at some numbers. So what is the annual global freshwater use since 2000? So annually since 2000. The figure I found is 4,000 cubic kilometers. And depending on the number, so that would supply water for 25 to 250 years. Which I had my first thought, oh, that's not too much if it's not renewable. But this is due to a very sparse database we have on these figures. Yeah, but this is one of the major questions. How much OFG is there? What are the mechanisms of emplacements? Can it be used sustainably? How does OFG respond to extraction and climate change? What are the legal issues? So the bold ones is what we can aim at with geophysics. The others are questions from the other off-source working groups, right, Hamid? So these are points you are looking at, you are addressing. The motivation should be quite clear. Most of the world population live close to coastlines. There's lots of overuse. There are mega cities. There's lots of industry along coastlines. So the pressure is high on groundwater due to population growth, climate change, and increasing populations. Another interesting paper by Daniel Zarmsky, I heard is pronounced Zarmsky, He's a very dedicated hydrological modeler. He's done these other 2 training schools. And well, the left figure shows, you see 2 colors along the coastlines. The outer ones is an calculated estimates of offshore fresh and groundwater estimates. Yeah, dark colors, there's a high potential for offshore fresh and groundwater. And the inner green colors are numbers for estimated numbers for onshore groundwater abstraction. So how much is actually used. So what he's comparing here is if there's enough groundwater where it's actually used, where actually a lot of demand, where it is used as well, to see where high risk areas for water usage. The right color shows the same for the offshore fresh and groundwater potential. And the inner colors, green, yellow, red, shows the demand. So difference between what's actually used and what's the demand is. So that goes more in the motivation to look at offshore fresh and groundwater. And this is a figure from a nice paper of Brett Weimer from Nature, Communication and Environment 2022. Back to the geophysics, I mentioned to look at offshore fresh and groundwater. We're looking we're interested if we have a connection of the OFG with the land of OFG. That means we have to look at the whole picture from the coastline to near coastal, up to offshore, actually up to the shelf break where we go in the deeper basins. This is the area we will have to tackle, and these are some of the methods we can use in the different areas. So we have to, if we are considering a workflow, we have to look at the best methods which work in which area, which can be worked from the beach, which can be worked from the shallow coastlines to the deeper offshore areas. Well, deeper for this target means up to 100, 200 meter water depths, because then you are again at the slopes and we're looking at other processes. And yeah, that's what we partly look at in the next slides as well. So on land, this is our terrestrial time domain electromagnetics. Magnetotellurics, I will not talk too much about that, but you will see it on some of the slides. Magnetotellurics is a passive electromagnetic methods where you don't use active source and where you can look, where you get resistivity information up to deep levels, up to kilometer depths, depending how on your measuring site and how you set up your array. Yeah, so that's just to have that heard, have that in mind. Seismic reflection, you will get a lecture on that tomorrow. Semi-airborne CSEM. This is actually a new method which has been developed at the LIAC Institute in collaboration with other universities here. Semi-airborne is a mixture of ground geophysics and airborne geophysics. They use receivers which are flown by a helicopter and large transmitters which are based on this on the ground. The advantage is you can combine the large coverage you get with airborne methods with deeper penetration using a grounded transmitter source. Yep. Marine CSM, that's the field I'm working in. We'll see some of that. Satellite gravity magnetics, I will not talk about that. Marine magnetotellurics, all the geophysical methods we're going to talk about in the marine field have been originally developed for land application and have been adapted to sea application. I'm showing here tables from a paper we are currently putting together as part of our working group 2 from the off-source paper. The aim of this paper to provide descriptions of best practices to develop a workflow for OFG exploration, looking at what kind of different methods are there. And this is a table for different methods for seismic data acquisition. And important for you to know is that these methods can be adapted to look at shallow depths, to look at deeper depths, whatever is required for your target. Yeah, so there are offshore methods which use high frequency and have highest resolution in the upper tens of meters. There's large seismics which can look up to kilometers down the sediments. And that's what we have for the seismic methods. For the hydroacoustic methods, that's a table which has been put together by Ilian, which I can actually look at the water columns and at the shallow sediments. Hydroacoustic methods are mainly ship-installed tools, while seismic methods are outerboard tools. See a bit in that as well. And here for the ERT and CSEM data acquisition. And that's what we're gonna look at today a bit more. This is a very basic and essential slide for what we are doing. So talking about the electrical resistivity, about the parameter we are looking at. So it's a parameter which ranges for natural occurring rocks over a large range of magnitudes, what you see here. Yeah. So natural rocks, we have almost 10 orders of magnitude. And what we are looking at is here. So we are looking at basically at the saltwater, freshwater differences. So the electrical resistivity we are looking at, it depends on the sediment porosity and the pore fluid resistivity. And that in turn depends on the salinity. So here we have how a sediment could look at. We have the sediment grains, which are itself insulating. So no conductivity. Conductivity is the reciprocal of resistivity. Yeah, I probably use both parameters, both terms in my presentations. The matrix is insulating. What's conductive is the pore water. That depends if it's saline or is it not saline. So fresh water has low salinity, high resistivity. Seawater has high salinity, low resistivity. And we can use seawater libraries to calculate salinity from conductivity measurements or resistivity measurements, and also can use other models the other way around, calculate salinities, conductivities from salinities. This is the formula all EM and ERT people love. They are not getting away with that, with Archie's equations. It's an empirical equation which relates the formation resistivity, so of the whole package, with the pore fluid resistivity, which depends on the salinity, the porosity, and a factor of M, it's called sometimes cementation factor, and that tackles the shape of the grain matrix. Yeah, it's a bit of a range where it can write. If you are in, well, if you have clays, the world looks different anyway. But if you have more shaly, flat grains, you get anisotropy, so a dependence of directions of your conductivity. Yeah, that's an important factor as well. But the main dependence of the resistivities we get from our CCM data is porosity and pore fluid resistivity. That has the main effect on that. And that what we can show with such a figure. We have here the pore water salinity ranges, practical salinity units, and the formation resistivity here. And here we have it for saline, brackish, freshwater salinities. And these are Archie's law relations for different cementation factors and for different porosity values. So how we can use that, we'll probably see that later. Seawater has mostly conductivity of 3 Siemens per meter. Shallow seafloor sediments of 1 Siemens per meter. The other way around, or seawater 0.3 ohm meter, which is the unit for resistivity. Seafloor is about 1 ohm meter. So that's the difference. So here we are, 10 to the 1, we are a bit above 1 ohm meter at a porosity of 60%. For seawater, we have salinities of 33, 35 Siemens per meter. If we have salinity, pore water salinity of 3.4 PSU, a porosity of 60%, we arrive at bulk resistivity of a bit above 1 ohm meter. If we have brackish water and higher porosity, say here it's maybe 40%, we arrive at bulk resistivities of 1, 2, 3, 4, 5, 6 ohm meter. So that's how we can use this Archie's law. Okay, to start it with a basic control source EM principle. In this example on the left side, we have an electric dipole transmitter on the seafloor, and at some offset, we have 2 receiving dipoles, this electric receiving dipole. We measure the inline component of the electric field. Yeah? So electric field is a vector, but we only look at the horizontal transmitter dipole and receiving dipole. If we inject currents in the transmitter dipole, they propagate especially in the seawater and in the more resistive ground. And the signal is picked up by the receivers some distance below. And from this information, we can refer a resistivity structure at depth. Yeah, we will come to that again a few times. So in this example, we have both transmitter and receiver on the seafloor. We can have them anywhere in the water, towed in the water, or towed at the seafloor, towed at the sea surface as well. Another way to look at that, here it also shows field propagation of a horizontal electric dipole on the seafloor, which is here. You have seawater above, seafloor here, sediments. Here you have a electric dipole, and we look at the field propagation in 2 steps of time here a bit later. And that's what we call a background model without an anomaly. And here we have a resistive target layer. It's not a layer, it's a 3D structure, actually, which has a resistivity of 10 ohmmeters. It's more resistive. Could be a lens, let's say a groundwater lens. I use that once for gas-hydrate studies and at a deeper layer. And if we look at some distance of 500 meters, if we would have a receiver here at the seafloor, it would see something different when we have a resistive target here, right? So we would like here at that point of time with the background value, it's a model study, it's a synthetic model study. And here we would see, here the signal didn't arrive yet, and here it's much closer. It's influenced by the presence of the resistor. Yeah, so bit of basic concept. Now we come to an overview of the marine electromagnetic and ERT systems which are used in OFG. So and I will talk about these different setups. So there are different setups we can use for OFG studies, which is for CSEM data acquisition. We have surface towed systems, we have seafloor towed systems, deep water. We have a mixture of stationary OBM, ocean bottom electromagnetics. So it's a stationary sensor systems with a deep towed source or some hybrid systems. For ERT, we look at data acquisition for surface towed, seafloor stationary or deep towed as well. And this is a figure in process we would like to use for our best practice paper we are working on, where we have Lina, you probably know her. You know her? She's from Malta.
Sorry?
Do you know Lina Jacquete?
Lina, actually, no.
Oh, okay. I thought it's a small island and everybody knows it.
Yeah, I don't know.
Where we try to image all these different systems which can be used, some on the seafloor, some surface towed. Some will work more to coastal areas, some will work further offshore. Yeah, so these systems differ in penetration and resolution depths and in the logistics of operating them. So I would like you to get a feel for that as well, what it means logistics-wise to do these measurements at sea. I will talk about electric dipole-dipole systems where we do controlled source EM. And it's in the name, electromagnetic. You can generate the signals electrically or galvanically with dipoles, but also with magnetically with loops or with coils, right? And that's what Pritam will talk about more in the afternoon. He will use loop systems, coil systems to generate electromagnetic energy or setups. There, I was mentioning that we have all these different systems and setups, but there are differences if you look for conductors or resistors in the seafloor. Yeah, so depending on how your configuration is, they not all work for all kinds of targets. Or if you look at mineral exploration, sulfides, ores in the seafloor, you would look at different systems than to looking for resistors. Typical applications has been oil and gas exploration. Oil and gas are resistive, gas-hydrate exploration, and the systems which we use now for OFG has been adapted from different applications. That's something. They have not been particularly designed for OFG, but they have been adapted. So most successfully used systems for OFG are surface-towed CSEM systems. That sounds like there are many around. Actually not. I know only of 2 systems in different, two institutions who are running this systems more or less. The setup is you have a research vessel, and behind that you tow an electric source dipole, and in some offsets you have receiving dipoles. This system has been developed by the Scripps Institution in San Diego, and it has been used so far offshore New Jersey, in Hawaii, and in the San Diego Trough. The system measures the inline electric field at 4 receivers at a short 2-meter dipole, some sampling rate. The offset between transmitter and receiver define your resolution depths, your penetration depths. Having measurements from several offsets increases your resolution at depths. These offsets can be modular. Yeah, you can extend the offsets or make them shorter depending what your target area is. They are towed at a speed of 2 to 4 knots at the surface. 1 knot is about 1.852 kilometers per hour. So a bit less, 1 knot is a bit less than 2 kilometers per hour. It's pretty fast. And here just some numbers, what has been used in this surveys. So this is for the system. There is has been a similar system developed at GeoMar. GeoMar is a marine research institute in Kiel in Germany. These are some figures I found from the New Jersey survey. A big seismic vessel was used to run this survey. You see here the streamer going out in the water. There are buoys to tow them on the sea floor. This is how one receiver looks like. These poles hold receiving electrodes at each end. In this whole tube, you have the data logger. If you work at sea, in seawater, every electronic has to be pressure proofed in pressure vessels. There's also a float. They are floating. There's a rope with a buoy attached to them, which hold the whole thing at the surface. And to get the position exactly between each component, there's a GPS connected here. And these receivers they are autonomous working, and they're just connected by simple rope, which means during a survey you cannot communicate with the systems, but you can actually see them. That's a nice thing here, so that if they're floating or not, and you get the GPS position. Here's again a figure. So in front you have the transmitter dipole to produce the signal and the energy. You have a transmitter power supply and controller on the vessel. These are some results. So this is actually I think one of the best and well-established case studies which exist so far on offshore fresh and groundwater. Offshore New Jersey, there have been several drill sites. There has been an IODP leg 313 in 2009, which drilled 3 sites along the New Jersey coast, where they found low salinities, less than 3 grams per liter at 400 meters below seafloor. These are other drill sites. The yellow ones show low salinities and the purple one show high salinities. That's all from Chloe Gustafson's paper. Yeah, here are the resistivity logs where you see the freshwater intervals. There's interpreted seismic in the paper from Lofi et al. 2013. And based on that, you have here interpreted phases based on the seismograph. So sediment phases distribution derived from core logs and seismic profiles show units of alternating permeability, hosting low salinity pore water in fine-grained and saltier pore water, and saltier pore water in coarse-grained intervals. That's the main result I got from that paper. And here you see the results from marine control source EM plus MT. That's this passive method which constrains the deeper parts of the model and which can be jointly interpreted or inverted. Yellow colors show high resistive features, blue colors show more conductive features. So the main result is that they found this very resistive this anomalies here, which they overlaid with the seismic interpretation and which they interpreted as a groundwater reservoir, which extends 90 kilometers offshore New Jersey using this system. So what I want to talking about geophysics, here you have seen just a result. But what I want to make you a bit sensible for is how to read such images of when you see resistivity models. Electromagnetics is not a high resolution method. You get volume information from that. With electromagnetics, you will not get this structure figures as you get from seismic. But how these two methods work together is that you get the structure from seismic and you get the volume information from EM methods. Usually if you see such papers, you will see one model here. But this model is the result from a whole parameter study, which comes up that this is under certain assumptions the best model you can get from the data, or what you can interpret from this data. What EM cannot do is get any resolution of inner structure. So EM does not resolve fine inner structure. For modeling reason, you have to make this numerical model, this numerical grid behind this very big. So which part of the resistivity model do you show in your paper and your presentations? It depends how much can be resolved from your data. Here I'm showing some data fit of the data which they used to get these models. So you see there at larger distance they get quite noisy. So but actually they're showing data fit. So that's kind of a control how well the model fits the data, if it's a valuable data. So that's something to consider if you look at these kind of resistivity model. How well are they prepared? Because you will always find a model that fits your data, but how geological reasonable is the model? These are the seafloor towed systems, which I brought to Germany from my time in Toronto. We used this system a long time to look at submarine groundwater, submarine gas hydrates, sorry. Also resistive methane gas, which clogs in the shallow seafloor sediments. Similar setup, but the whole thing is on the seafloor. Yeah, it's also the electric transmitter followed by a number of receivers. The systems are modular. We use maximum of 4 receivers. We can use less, we can use more. We use similar offsets up to several hundred meters. But there's a number of challenges to that because we do this on the seafloor sediments. We drag them through the mud, so they have to be very robust, the systems. It's quite a risky business if you don't know your seafloor conditions very well. But the advantage is that we use much lower source dipole moments. We can get the same data quality with less currents that we inject because we don't have to look through the whole water column. The other thing is we don't have to tow continuously. What you have to do with surface towed systems, if you stop the ship, the system will sink. Here we know that in places of interest where we have to get higher stacking, collect more data. We can do that by stopping the vessel and keeping position with the system. But of course, we have to do way more maintenance, way more attention how robust the signal is going to be. And it's very slow. But compared to the surface system, we get a much higher data quality. So these systems are towed along profiles on the system. If we do another profile, we usually bring it up in the water, turn it around, lay it out again. It takes a whole lot of time, which is.
Sorry, one question. If you go back to the previous one, this is in the sea bottom, but you mentioned survey speed 0.51 knot. That means that you can move the cable in the sea bottom, or?
Yes, we move it, we drag it. Oh yeah, yes.
We're moving the whole line.
Yeah, that's what I'm thinking because some ERT systems, which work more coastal, in the coastal area, they are surface towed or sometimes they are laid out on the seafloor. And I just wondered, why don't you drag them? It's just, even for near coastal work, there's not a lot of weight you have to do this. Here we have to, we call it a pick. We have a big weight in front of the system, which kind of is like a plow, which keeps the system on the seafloor. We also have transmitter and several other sensors in here, CTD we have on the pick. But you don't have to do this if you work with ERT systems on the seafloor. So I just wonder, why don't you drag them and get whole profile lines?
Because some places you cannot drag systems.
True. We have done it. I don't recommend it, actually. We bring energy down, high voltage down, transform it into high current. The transmitter we can operate from the ship. Yeah, we operate that from the ship. We have different systems. We used to use the streamer behind as a black box. There are data loggers to connect to that. So behind each data logger is a dipole, 15, 20 meter long. Each data logger has a high precision clock. We need a very exact time base between the source signal and the receiver signal. They are synchronized prior to deployment. And then you bet that they keep the time base. We have some things we can do about that. And then we bring the whole thing down. We have acoustic positioning to know where the system is. In shallow water, it's not 100 meters is shallow for me, very shallow. We use it in 2 kilometer water depths. So then the system is 4 kilometers behind the ship. GPS doesn't work on the seafloor in the water, just to let you know. But hydroacoustic works. So you have hydroacoustic transponders attached to that, and you monitor that from the ship. Such a system might be interesting. The surface towed systems I just showed before, they have resolution. So they have been operated so far up to 80 meters of water depths. So if you want to go deeper, you either have to bring more energy down, which has not, as far as I know, hasn't been done with surface towed systems. So you have to bring your whole area closer to the seafloor. These are academic style systems. You cannot go somewhere and buy them. And anyway, all these systems I'm showing here are mainly developed by research institutes. So there is no industry behind that. With ERT system, it's different. But all these systems come from academic institutions and have been adapted to more or less through each project where you see data here. We use the system in the Canterbury Bight offshore New Zealand. That's off a bit south of Christchurch on the South Island. There have been an IODP, Integrated Ocean Drilling Program, if you're not aware of that. Scientific drilling, not dedicated to groundwater, but they have found a low salinity, low chlorine in pore waters at about 50 meters below seafloor at this site here. Not at that site, at this site here. So that gave motivation to go there with electromagnetics. This was part of the Marcan project, an ERC grant, European Research Council grant, coordinated by Aaron Mikalev. And we cooperated with the Research Institute in New Zealand, NIVA, and had ship time on the Tangaroa, that's the New Zealand research vessel. And these are the survey lines we did with the seafloor towed systems. And they were also covered by seismics. Again, we have the reflection seismic here, which has been converted to depths as I see it here. And here's some interpreted facies analysis on the seismic sections. And these are the results from the CSEM. So these are the inferred resistivity models inferred with the seismic interpretation. Yellow colors show high resistive zones, blue colors conductive zones. The main finding is a so far unknown pressured groundwater systems. That's how these data have been interpreted. The conclusions drawn from that findings, then the colleague went back to calculate salinity models from the conductivity models, assuming different porosities, a rather wide range of porosities. So because the resistivity could also be affected by porosity, as we saw from Archie's law. The conclusion here is that the resistivity models cannot be explained by porosity variations and lithology alone, but a likely explanation is that we have freshened pore water, blue colors here in that systems, which can explain the resistivity distribution. So here I just put a mosaic of different images from being at sea. Again, here we have the survey configuration. That's the vessel, about a 70-meter former fish trawler, which gave us a bit of a challenge to deploy this system. You have to have a plan. How do you deploy such a system from a vessel? And usually you do it through the aft, where you have a movable A-frame. So there's a big crane which has the shape of an A, which you can turn out. This is not the case here. It has just a stable A-frame. The whole area was about 700 meters long, and obviously you start deploying from the back. Don't drop the pig first, pig comes last. You start deploying from the back. And while you deploy the system, the ship has to move forward, otherwise you dump everything on one place. This was a system where it was just only connected by rope. So you have hundreds of meters of rope piled up here, figured of 8. These are is the electronics of the data loggers. Here you have high precision clocks on. The data loggers are into pressure vessels, and which are then in the fitting, which are connected to the dipoles. You see a bit of a dipole, and which are again connected with this rope. That all goes out in water. You need we had to bring our own winch to operate the system, which is this one here. So this is the tow cable, it's here, deploy it here. The whole thing is operated from a data center or from the lab. It requires very close communication with the person who drives the winch and with the bridge. So you can, if you tow the seafloor, the system can get stuck. You have tension meters on your winch cable, so that affords at least 2 people who permanently observe the system. Same system within the same project was used offshore Malta. Also, seafloor towed. Here you have the island of Malta. It has a carbonitic shelf region, offshore region. These are the profile lines we surveyed during this project. I only show results from line number 9, where we have here the seismic section and the interpretation with this different limestone units. And that's the result from line 9 from the resistivity measurements. Different color scale. We also sensitive what the color scale shows, if this is a reasonable range of values, what it shows. Red colors are conductive, blue colors are resistive. And the target here is this resistive, rather small anomaly here, R4, which has been interpreted in Amir Haron's paper as a disconnected and relict OFG body by emplacement during sea level low stands. But the methods which has been used here is multi-channel seismic, CSEM, core log data, which are actually onshore, and hydrogeological modeling. Also some images here. I have to say, I never worked on such a small vessel. Xavier was there as well, with all this hundreds of meters of cables. Do you know that, the Hercules? You know it.
Yes.
It was quite a challenge to bring all that on this little boat. Here you can see our tow winch. Front of it is a spooler that we don't have to take everything in by hand, which we actually did. Luckily, we were lots of people. That was only day cruises, so we didn't stay on the ship. That would probably have exploded the capabilities. Yeah, here you see Martin, a technician who's soldering or building some last cables, while this is you, Javi, sleeping, relaxing, and having discussions how to deploy things, setting up the receivers, sitting on 6-pack of water bottles. So it was a nice experience. Most important person on a vessel is who? It's not us, it's the cook, of course. That keeps us all happy and alive. So we get nice lunch. Yeah, and here I ask you, there's something wrong with this figure. Maybe you have an idea. it's not all wrong with everyone, but with some people, something is wrong here. If you have heavy equipment moved around on ship, you wear hard helmets. Was a bit more relaxed there. Safety first on vessels. And we had this wonderful scenery coming back every day, so the skyline of Malta. This is a more unique setup. The University of Cologne, Amir Haron and Klaus Lippert applied off the coast of Israel. I would call it semi-stationary. We're looking at the depths of an aquifer extending out to the sea. They were placing receiver dipoles on the seafloor, connected to floats at the surface, and towed differential electric dipole by a vessel. Here's some technical information on that. 25 amps times 400 meters, so pretty long differential dipole. 50-meter inline electric fields with two receivers, RX1, RX2. Offsets between the transmitter and receivers were 370 to 580 meters. Positioning with surface buoys. Operating water depths 20 to 25 meters. And those were kind of single site measurements, quasi-stationary, as the whole area was then moved from site to site. So that's rather slow, but looking at more detail at this offshore target. In the middle, I'm not sure if that was a pipeline or something else, they had a no anchor zone, so where they couldn't tow across. So they had one part of the survey from the beach up to here, and then had to redeploy the thing here. And I think it took several days to collect this data. Results here as 1D stitched inversion models, 1D. So each site is single, as a 1D model inverted. Yellow colors, again, resistive, pointing at fresh water. Blue colors, conductive, pointing at saline pore water. Interpretation is that they could show the aquifer, the freshwater aquifer extends up to about 3.5 kilometers away from the shore. Seafloor penetration depths, about 500 meters, require measurements at the seafloor and or large transmitter moments and large TX RX offsets. Something we were talking about in connection with the surface towed and seafloor towed as well. Before I forget to mention that, later, we were talking in the beginning in the motivation that of particular interest is the onshore-offshore connection. Some call it the white ribbon zone. Yeah, so if the connection is, if of offshore aquifer connected to do the onshore ones. And that's also a gap of how we can get data. So we can do measurements on the beach, up to the beach zone. We will see this afternoon that there are ERT methods which work in very shallow water, looking at submarine groundwater discharge, saltwater intrusion. Those were the systems which were used there, together with shallow-looking hydroacoustics. We have equipment we can use offshore, which come from different applications to look at deeper targets in deeper waters using bigger research vessels, which can probably operate up to 10-meter water depths. So, but then we have this gap where we cannot go with with the big research vessels, and where we have systems which can operate maybe from zodiacs or rubber boats, really from small scale boats, but they don't look that deep. They resolve maybe the upper 50 meters. And in that areas, such systems which take more effort will probably be required to resolve the deeper part of the near coastal zone. That has been done by a synthetic model study by a colleague from Japan. So this is just a concept study to look at particularly at that part. And he suggests, or what he looked at, is a onshore offshore setup by placing stationary ocean bottom electromagnetic receivers, which are not connected by rope, obviously, which are stationary on the seafloor and measure electric fields in 2 directions, sometimes even 3, and also the magnetic field. Place them on the seafloor and on land. This is used for this passive magnetotelluric methods, but if you have a source, you also get active controlled source electromagnetic methods, and place a transmitter on the shore. And they simulated how far they can see well-resolved signals offshore. And that's the model they used. So here you have the shoreline, you have here the sea layer, quite simple model. And here you have a freshened water aquifer with 20 ohm meters. That was put in a numerical model. Don't ask me why it's now 100 ohm meters. That's how I got it from this paper. And this is the inverted model. So he generated a forward response. We will talk a bit more about that tomorrow. Synthetic. So he generated synthetic data from this model, put them in an algorithm, in an iterative inversion algorithm. That's the model he got. And with that setup, he suggests that he can detect up to 5 kilometers from the shoreline and an offshore aquifer. So that would be interesting to put this in a real experiment, to look again deeper part of the white ribbon zone or near coastal zone. Yeah, surface towed, seafloor towed, deep towed. Deep towed means still in the water. There have been different setups. That's the classics. In parts, it's the classic setup which has been used and developed for oil and gas exploration. This is a setup which has been developed for offshore oil and gas by a company called PGS in Norway, which has the dimensions of a large seismic streamer. So they, instead of having like a few 100-meter streamer, this one had, but they refurbished the seismic streamer and put electric receivers in it. Up to the original system, I think, was up to 6 kilometers long. So with much larger offsets to look at much deeper targets. And they decoupled the transmitter dipole, which was towed just below the surface from the receiver, but towed from the same vessel. To get data, they have a totally different story of dipole moment. That's several thousand amps, or the order of 1,000 and more amps they put in the water. It has been successfully used over offshore gas targets, but since energy resources are a little bit from the list, that has been then available to look at different resources like mineral resources or even offshore fresh and groundwater. So such a system exists, but it has, let's put it, open ownership at the moment and not ready to go. But not published yet. The Woods Hole Oceanographic Institute has developed a similar, somewhat smaller sized system. And that would be also another setup to look at this, to get deeper penetration depths offshore. But it needs, but this is for offshore. With such a system, you don't look at this white ribbon zone, at the near coastal zone. It's to get better resolution, better penetration depths further offshore. And then finally, I thought I'd put something in what we are doing. One setup we recently developed here. This is a test cruise we just did 2 weeks ago out of Kiel in the Baltic Sea, where there's actually some offshore groundwater discharge happening. We built 3-channel electric field receivers from the Scripps Vulcan design. I'm not sure if someone is familiar to those. Scripps is the marine EM lab at the Scripps Institute in San Diego, is the leading academic research institute for that kind of instrument developments and research field. They built the original Vulcan. Vulcan is a tow body which measures all 3 components of the electric field: the inline component, the vertical, and the broadside, so the cross component. These are towed at different water depths, measuring electric fields from a source dipole towed in front. Also a setup which has been used for different targets to look at resistive features in the seafloor, then usually at a larger scale. We rebuilt these E-field receivers, called them Spock. Different from Scripps application, we managed to get online communication and online data. That's something we talked about along copper cable. The future will there probably go towards using fiber optics, which exists. We use fiber optic cable to talk to our tow body here in front. So these are typically cables supplied by vessels. At least German research vessels have optoelectrical cables. That's not always the case. So you have power using the copper strings and communication data transfer using the optical fibers in the cable. However, using optical cables along such a line has a total different stories when it comes to connections. To have communication along such a line, you need electrical connections and you need mechanical connections. And since you have a lot of drag on such system, you need to decouple them. And that gives some challenges to design such systems. This is our tow body, originally designed for different type of measurements, but worked quite well. Behind that, we have just a pretty short 20 amps, 20 meter dipole. The telemetry unit, so which provides the power to all the other sensors and communication, and the signal generator are here in titanium pressure vessels mounted on this platform. It's connected to the vessel, and we have a cable along this line, which we lay out before deployment. And that's how our tow body looks like. So we have electrodes at each end at this post, and the vertical and the horizontal here. That's just a recent test, so I don't have any data, just the general setup, which could also be interesting for offshore fresh and groundwater. MAPM is a spin-off of the University of in France of Brest. The group has also a strong history way back using marine electromagnetic methods. And as far as I see that, they are the only commercial supplier for deep-towed ERT system. That's the general setup. This can be operated from smaller vessels. The main fish here, which you see here, hosts the transmitter, so the signal generator in that. And one of the current electrodes, the other current electrodes is as a second little fish. So here you inject, here the current is injected, and then you have here the streamer with up to 20 measurement electrodes can be combined to measure different dipole configurations. Thought I reduced the number of technical characteristics. That's towed close to the seabed, can be towed 1 to 5 meters depending distance between receiving electrodes, somewhere pretty close to the seafloor. The depth of investigation is so far in the order of 50 meters, but can be extended if you use higher dipole moments. It comes with on-site real-time data acquisition quality control interface that is used and will be used and further developed for OFG as well. And that's a recent publication offshore Turkey, offshore Antalya, looking at seawater intrusion using a surface-towed electrical resistivity tomography system. This is the system RESIX, which is developed by a small company in Kiel, northern Germany. But there are a number of different systems around, which are commercial suppliers like the Siscal system from Iris. So there are different suppliers for coastal ERT systems. In fact, it's a dual cable, which uses 2 different source dipole lengths to focus more on the shallow structure and deeper structure. It can be towed pretty fast. Here you see the geoelectric cable with the floats marking the receiving dipoles on top. The whole thing can be spooled on a smaller drum. Also different logistic efforts when you think about the big winches we use for deeper looking studies. Yeah, I can recommend to look at that paper. It has been combined with transient electromagnetic measurements on the coastline. And here are the survey lines of the ERT systems. And they found fresh water extending up to 500 meters offshore. I just showed some examples of the different CSEM systems and some ERT systems. But what we are looking within the cost action, within our working group, we collected a lot of information and on the different systems we know which are around, with contact persons, with the setups they have, what kind of source moments, pretty detailed information we tried to get from literature, from direct communication, and etc. So this is something we would supply to the community as well, so that you have an idea what's around, and contact, challenges, advantages, what can you do with the system, what not. So it's work in progress. This is for ERT. If you have some systems in mind which you don't find on our list, so please contact us that we can include that. So this is the MAPM system. This is not really I never worked with the ERT systems, but from literature, Siscal. This is a system developed in Japan, which is basically useful for OFG as well. I'm not sure. I learned from the floating system just at the swim conference. I heard the first time. This is a system which is a loop system floating on a little platform, and it's basically used to look at salinity variations along rivers. So this is, we put this on the list as well, but it's we think it's more useful to look at very shallow seawater. Yeah, this is a bit of a a summary with pictures from the geophysical methods for OFG. We will hear more about that, multi-beam sounding from ship-installed systems, sub-bottom profiling with, also hydroacoustic systems, multi-channel reflection seismics, usually using bigger research vessels. On the EM part, surface-towed ERT, CSEM surface-towed seafloor, or mid or deep water towed. So that's what we covered today. Again, that's one of the main messages. Bring these two methods together. We need both of them. But particularly for offshore fresh and groundwater, the hydroacoustic methods are blind to the pore water, to the nature of the pore water. They see the structure, but they don't see if it's fresh water or seawater. And that's the big plus or the big advantage of resistivity methods, because they're sensitive to that. Bring them together, so both methods gain knowledge from each other. Again, provide structural information in high resolution, but are not sensitive. Resistivity methods provide volume information, but you see that this blobby images. Be aware what you can interpret and what not. And both methods can be adapted to reach a wide range of penetration depths and water depths.